Hello, everyone. This is your host, Zaid Maher, from the Arab Culture Center of St. Louis in the state of Missouri in the United States of America. And this month is the Arab American Heritage Month. And we at the Arab Cultural Center of St. Louis are celebrating this month. And one part of our celebrations include a series of lectures on important aspects of our Arab American culture, but with emphasis on Arabic culture, Arabic civilization. And these lectures are hosted by us, and our guests are experienced and well-known academics in their field. Today, we have our first lecture on Islamic-Arabic Astronomy, which will be given by Professor Rihab Sawah, who is a professor of physics at Lincoln Land Community College in Springfield, Illinois. Before I introduce our guest, I would like to say a few words about our center and let people know who we are. Our center is a 501c3 nonprofit organization and one of only 3 Arab cultural centers in the United States to receive this designation from the federal government. The center is dedicated to fostering understanding and mutual appreciation between cultures by promoting awareness of the history, language, traditions, and customs of the Arab world. As a cultural center, we hope to become a bridge between different non-Arab cultures by promoting dialogue, mutual respect, and understanding. As an Arab center, we provide community support for individuals and families of Arab heritage, helping them integrate in and actively engage with the broader community of St. Louis and, by extension, the state of Missouri. Our vision is to create a welcoming and inclusive environment where members of the Arab community can connect with one another, share their cultural traditions, and celebrate their heritage. We are a multicultural center par excellence. We are multi-ethnic, multi-regional, and multi-dialectal, and our sense of identity is shaped by our understanding that being an Arab American means being both an Arab and an American, and that is the power of pluralism. As I said a couple of minutes ago, we are celebrating the Arab American Heritage Month, which was created by the US government a few years ago. It is the month of April. And a part of our celebrations is having this series of lectures. And our lecturer today is Ms. Rihab Sawah. I will introduce her to you now. I will try to be brief, although frankly speaking, it's hard to be brief when talking about someone as experienced as Ms. Sawah. I'm looking at her CV and I'm thinking, what can I leave out? But I will try to be brief. Ms. Rihab has a bachelor's degree from Damascus University in Damascus, Syria, in mechanical engineering, and then another bachelor's degree in mechanical engineering from the University of Missouri, Columbia, Missouri. And later she had a Master of Science in Physics, again from the University of Missouri in Columbia, Missouri. And finally, a Master of Arts in History from the University of Missouri, St. Louis, Missouri. This particular master degree, this very last one, is an interesting one and has an interesting The thesis has an interesting title, History of the Observatory as an Institution from Maragha to Mount Wilson. And this, if my understanding of Professor Sawah's lecture topic for today is right, this thesis is providing the foundation or the background of knowledge, if you will, for our for today's lecture. Ms. Sawah has worked at several community colleges in the state of Missouri. Moberly area, St. Louis Community College, currently at Lincoln Land Community College, and at all these she has been a successful faculty, physics faculty, who did not limit her teaching experience to the discipline itself. Ms. Sawah is known for having used or employed her skills in more than one aspect, talking about physics, but also talking about the importance of, for instance, the Arab Muslim contributions to physics and astronomy. Her lectures, especially her public lectures, combine what is rigorously academic and disciplinary with what is cultural in a more inclusive sense, in an inviting sense, frankly speaking. She as a speaker who is often invited to give lectures at many institutions, nationally and internationally. She is known to combine what is strictly academic with what is culturally inviting, opening perspectives, broadening minds, and inviting her audiences to think outside the box or the rigorous boxes of academia. One of the important things about her contributions, or one of her contributions, has to do with Arab Islamic astronomy and with Islamic civilization, and the great contributions that Muslim Arab scientists have made over centuries, and what they have provided humanity with, which has created the foundations for modern-day modernism. In fact, modern-day modernism is greatly indebted to the contributions of those great scientists and scholars who worked under the umbrella of the Arab Islamic civilizations in several parts of what is called now the Arab world and the Middle East and modern-day Spain. Ms. Sawah, her career spans about 30 years of continued work at academia and outside academia. She has received several grants, including Fulbright grant, and she has published on several topics, including STEM, science, technology, engineering, and mathematics. She has lectured on Islam and Islamic civilization, and I think I'm going to have to stop now and give her the floor, because frankly speaking, I could go on and on talking about her, but I will stop. I will now turn the floor, if you will, to Ms. Sawah. You are welcome. The floor is yours, and we are all listening. Thank you.
Thank you, Zaid. And thank you for the Arab American Cultural Center in St. Louis for inviting me to begin your your month-long series, right? This is the first presentation. So thank you for giving me that honor. I appreciate it. Just as a disclaimer, I'm coming out of a slight illness in the upper respiratory, so please don't be concerned that I might be coughing at times. I'm perfectly fine. So the title of this presentation is Islamic-Arabic Astronomy, and people ask, why is it combining the words Islamic and Arabic? And there's really no name that historians can give to the contribution of the era that is known as the Islamic era, where the recorded sciences during that time period was in Arabic. So that's why you often might see in history of science books reference to this time period as the Islamic or the Arabic science contribution to humanity. And I will share with you my presentation, and we'll talk and we'll converse throughout the presentation. If you do have questions, please post those in the chat. I will attempt to remember to look at the chat during my presentation, but if not, at least I'll have them at the end of the presentation, and I'll definitely address those.
Thank you.
So as I said, when we talk about the Islamic or Arabic contribution to science, and this talk today will be about astronomy, the reference to Islamic is because it happened under the auspices of Islam. So we're talking about the time period when Islam became or spanned as an empire, and it spanned as far west as Andalusia or Islamic Spain, and east as far as the Indian subcontinent. So that's why this time period is referred to, or the contributions of science during this time period are referred to as Islamic contributions of science. And then also we refer to them as Arabic contributions to science, because it was during this time period where Arabic became the language of science, and everyone who contributed, and we find people from different, not just ethnic backgrounds, and people who have as their mother tongue other than Arabic, such as Persian or even Aramaic, etc., Hebrew as well. They all contributed to this body of science that was recorded in that era in Arabic. And so that's why there's my mentor, the science historian, the renowned science historian, George Saliba, who's from Lebanon, tells me that we just cannot find a name that is befit of this era. So we often use the words Arabic or Islamic, sometimes even combine them or use them interchangeably. So if we look at the world map and how Islam within its first century basically spread east and west, it brought along with it not just the religion and a way of life and culture, and that's just the nature of how civilizations get to know one another, but also what happened during this time period, what we call the Islamic era, is had a great influence in the sciences. So this was a time period when there was an enormous translation from the ancient Greek sciences. And by the way, that's how ancient Greek sciences were preserved, by being translated into Arabic and being preserved. And of course, when we talk about translations of science, it's never just about translating a body of science, but especially under the Islamic era, there was challenging of a lot of these ideas, and even maybe not just altering some of these concepts and philosophies, even, as we'll see in a little bit, but also modifying and or replacing old ideas with new ideas. But basically what happened during that the few hundred years after Islam came, and the mass translation of the entire body of science during ancient Greek science became preserved in its Arabic form, that eventually made its way into Europe and allowed for or contributed significantly to what we refer to as historians as the Renaissance. So I will refer to names of centers of science, such as Baghdad. Of course, it was the renowned center of science during the Abbasid time. This was when we see universities emerging. The concept of the university as we know it in its modern form really dates back to that time when we talk about Beit al-Hikmah in Baghdad. And then, of course, we have Damascus and Cairo moving westward all the way to Cordoba and Granada. So this is geographically, we're talking about a really vast region, but yet science was able to make its way from east to west and back in a really short time, but not only in its written form, also in the form of how scientists themselves would traverse the distances to actually play significant roles, as we'll see in astronomy, in the development of these sciences. I will specifically also refer to some of the further east centers of science. I will talk about a center of science or a center of astronomical science, specifically astronomy in Maragha, which is in Persia, to current day Iran. And in Maragha, we'll see a very important development that really changed the face of astronomy and allowed astronomy as a science in its modern sense and its modern term to emerge. And then also to Samarqand further east. So, as a scientist myself, I teach astronomy in addition to physics, which is really my main discipline is physics. But when I open any astronomy textbook, college, university textbook, there's always a gap, a huge gap that happens between what the Greeks introduced, the body of astronomical discipline during that time period that really happened between the era of 500 BC and 200 AD. This is really what we know as the golden age of astronomy specifically, since it pertains to our presentation today. And then there's a huge jump from 200 AD all the way to the 15th century, and mention of Copernicus, who brought along what is known as the Copernican Revolution in modern historical terms. As if what happened in between was completely a desert. And there's very, very little, if any, mention to the contributions of Islamic science to astronomy during those 1300 years. And, as a scientist, I can tell you that science doesn't evolve or develop that way. There's never a jump that spans hundreds of years and all of a sudden a new concept or idea or theorems or even a paradigm shift. Paradigm shifts don't just happen over someone contemplating them, but it comes about as changes that occur over a long period of time that perhaps someone eventually sees the need to introduce a new idea and hence a new paradigm shift. So during this time period that we refer to as the Islamic era, what emerged as the language of science was the language Arabic. Just like today, the language of science internationally is the English language. And so everyone learns English so they can review publications and they can even publish in this language. Back during the Islamic era, the language of science was Arabic. So regardless of someone's mother tongue, they would contribute to the body of the science. So in terms of what publications they would present, in the language Arabic, even if their mother tongue was Persian, or if it was Hebrew, or if it was Aramaic, or any other language. And there were scientists that spanned the globe, basically, even Chinese, who contributed to Islamic science during this time period. And specifically, we're going to focus on astronomy. So if we take a look at this publication that is of Ptolemy's body of, let's say, commentary on the observations, astronomical observations, that, by the way, the Greeks inherited from the Babylonians and did not do their own entire body of astronomical observations. Ptolemy's work, which is really a huge body of work that the Muslims translated, and again, I say the Muslims, I don't really mean specifically the Muslims, but those who were under the Islamic civilization, including Christians, and especially, Christians who were very well versed in the Aramaic language. They were able to also do translations from the ancient Greek to Aramaic and then eventually to Arabic, but also Jews as well. And so the work of Ptolemy, so we're talking, the early, in the first 200 years of our current era. So Ptolemy's work was preserved in its Arabic form. And this particular page shows us an example of how his work was preserved in the Arabic language. And it was known to the world by its Arabic name, which is Al-Majasti. And so even though this is a body of ancient Greek science, it was preserved in the Arabic language, again, because Arabic emerged as a language of science during that time period. And there were Muslim caliphs who would even give or offer, whoever would translate, of course, translate accurately, any body of science from ancient Greek. They would actually give the weight as a reward to whoever would do the translation. They would give the weight of the manuscripts in gold as a benefit to the person who does the translations. We see during this time period also a very keen interest in astronomical tables that would catalog all of the observations of, at the time, of course, the very visible planets were only 5 planets, and of course the sun and the moon. So we're talking about Mercury, Venus, Earth, obviously, is, we're doing observations from planet Earth, and then also Mars and Jupiter and Saturn. The other planets were not visible until the invention of the telescope later on. But also cataloging the stars in the heavens, and was all very important to astronomers. And the Greeks themselves, as I said, they had inherited the Babylonian astronomical tables, and that became problematic to the Arabs and Muslims during the time period that followed the translations, because they recognized that their current observations, even though they were not recorded in an entire body like Al-Majasti itself, but they varied from what the Babylonian observations were. So we begin to see other cataloging of the stars and the planets. And, here's one example that shows up in its both Arabic and then also translation into English, which was this version specifically was used later on in the Flamsteed Observatory in England. But we can see this very keen interest in what we refer to as astronomical observations that are cataloged of these bodies that I mentioned, and also the stars. But if we consider the bodies that are beyond Earth, like Mars, and then we go further out to Jupiter and then Saturn, we're talking about just to observe one cycle of these planets that are further away. The observations cannot happen within a year or 2 or 3, but they need longer periods, such as 30 years. And that's what was really needed to produce a new body of observations and catalog them so that they would match current observations. Because our planet Earth, we say it precesses in physics, meaning the planet itself, it rotates about its axis, but this axis itself, it also precesses around, and it completes one full cycle over thousands of years. So when we talk about observations that date back to the Babylonians, there is definitely a huge discrepancy with observations that the Muslims and the Arabs did during this time period, and a great need for new observations to be cataloged and recorded. So the earliest tables that we begin to see were by al-Battani. He definitely did not like what he saw in the ancient Greek astronomical tables. He definitely noticed great discrepancies, and even though Earth's precession was not necessarily known as a physics phenomenon back at that time, they understood that the locations of the planets and specifically the stars in the background were very different from what they inherited from the Greeks. And so he did observations, al-Battani, over 41 years. And his observations were so accurate, remarkably accurate, that they actually were very close to observations from our modern era. So we're talking, back in the 9th century. So it hasn't been yet a few thousand years for discrepancies to show up very significantly due to Earth's axis precession. So when we look later at Renaissance and later astronomers in Europe, we find them all quoting al-Battani because they actually used some of the astronomical tables that he produced. And of course, later on, we'll talk about some of the other bodies of astronomical tables produced in the 13th century. So let me give you just a really, really brief description of the ancient Greek cosmological model. So in the ancient Greek cosmological model, Earth is at the center of the universe, and all of the planets and the sun and the moon and the stars, they all basically rotate around planet Earth. And the model that was introduced, which was preserved by Ptolemy, Ptolemy is the latest significant astronomer that in history of science we talk about, and we mention his contributions. This is how the model of the cosmos was for the ancient Greeks. That if you have Earth being at the center, then you have crystalline spheres that are centered on Earth, and the stars that we see in the night sky are fixed on this crystalline sphere. So, and the crystalline sphere basically rotates around Earth, and that's how we see the stars rotating in the night sky. When it comes to looking at the closer neighbors, and I'm talking about the planets, the sun and the moon that are in our solar system, then the way that they were able to picture or depict their motion is that they were basically moving on what they refer to as different epicycles. The epicycles were actually attached to or sandwiched, you would say, between what they call the different shells. So the shells are you may refer to them as they're transparent shells, right? So that we can't really see the shells. What we can see is what's attached to the motion of these shells. So the shells themselves rotate, and these are called the deferent shells. So these rotate, and then the epicycles are rotating within the deferent shells, and that causes the apparent motion of the planets, the sun, and the moon. And of course, with the crystalline lens, then that motion allows for the fixed stars. And they literally viewed the stars as being fixed on this celestial sphere, which is also a crystalline shell. And then the shell itself moved, and it moved the stars in our night sky. So that's how we would see that motion. And so this is the cosmological model that the Muslims and Arabs, and again, I'm talking about Muslims and Arabs. I don't really mean specifically Arabs, and I don't specifically mean Muslims, but everyone who contributed during this era, are in this, are included in this naming. That when we refer to Islamic or Arabic or Muslims and Arabs, I really mean everyone who contributed to the body of science during the Islamic era. So what was really problematic with the ancient Greek model, especially when the Arabs started to translate the body of astronomical science into Arabic, is they recognized what Ptolemy had introduced, and he himself recognized the problem in that. He said that all of these shells, so these circles, actually move about a point that he called the equant. Now, you've probably all, at least if not played ball at some point in your life, you've seen others do that, right? And so if we look at any ball, right, a basketball, any kind of a ball, if you take that ball and you begin to spin it and rotate it, you can only balance it on one finger if your finger was right below the center of the circle and not under a point that's off center. So what Ptolemy had suggested, and Ptolemy had to do that, and I'll explain in a little bit why he put the equant off to the off center, basically. He recognized that it's physically impossible for any sphere to rotate about a point that's off center. But he was forced to do that mathematically because there are times when some planets, which are very visibly, we can very, very visibly see the difference when they are closer to Earth and hence appear really, really bright, and other times of the year when they're further away and they appear a bit dimmer. And so Ptolemy had to then make all of these spheres rotate about a point off center, which is the equant, and so hence when the planet is at its closest point, it appears brightest. And then when that planet was the furthest away, when its closest point, on this side of Earth, it would appear the brightest. And when it's at the furthest side, then it would appear dimmer. And he basically left it to future astronomers to solve this problem. How can you have physical spheres rotating around a point that's off center? Was very much a problem. And that introduced other problems into the model that we refer to as the ancient Greek cosmological model. So I won't get into those details, but those who were in the Islamic and the Arab world started to translate these, especially Al-Majusi, which was the most important body of astronomical science at the time, recognized some major problems, which really raised some big flags for them. So one of the scientists that emerged during that era, who really contributed to, I would say, a major shift in astronomy, was Nasiruddin at-Tusi. And Nasiruddin at-Tusi's fame was so known. He lived in Persia at the time, but his fame was so known that it reached as far as China in the east. And so when the Mongols swept through and they reached that region, which is current day Iran and Persia, they knew that that's where Atusi lived, and they made sure to let all of those who were in their military and their army to know to preserve his life and all his books, because he was very, very important astronomically speaking. Now, you might say the Mongols and astronomy, why were they interested in astronomy? It was mostly their interest in astrology that really prompted them to uh, preserve the life of Atusi, make sure that all of his science, all of his knowledge is preserved, all of his books. And then, of course, because they wanted to get an astrological prediction from him as to when they would, raid one region or another. And, Atusi is known in Iraq, especially because the Mongols relied on his astrological predictions in order to enter Baghdad and sack Baghdad. And so, yes, he's an amazing astronomer and scientist, yet, from a different perspective, he might have a different legacy that is not so necessarily pleasant for people in that region. But to mention what the contribution of, or one of the contributions of Atusi that were very, very significant, is that he introduced a new mathematical theorem. Now, until that time, all the mathematical theorems were mostly relying on what was translated from ancient Greeks, and then trying to fix the problem of Greek cosmology, the one that I mentioned to you earlier, without any success. But when we arrive at the 13th century, the latter part of the 13th century, and we come to this very amazing mathematician and astronomer, Nasiruddin At-Tusi, we see a solution that was presented that forever, and I really mean it, forever, changed how we actually view astronomy. It opened a new door. It beckoned in a new era. This new theorem that is known as At-Tusi's couple. So I want to spend a little bit of time talking about At-Tusi's couple and explaining it in as simplest terms, just so that you can really appreciate the enormity of it. So At-Tusi published his book, published his theorem in his book, which is At-Tadhkira fi Ilm al-Hay'a. And what you see here on the left is a modern publication of it. Actually, I wasn't able to even find volume 2. I only have volume 1. And it was Rajab who published it. And if you open this book, one side is literally the work of At-Tusi, not of course in his handwriting, but in print. And then the opposite side is a translation of it in English. And the image that we see on the right side here is actually a diagram of Tusi's work that is held at the Vatican Library. So I'm going to spend some time telling you about these circles because they are very significant and important in the development of what eventually became known during At-Tusi's era, and he actually gave this name to astronomy to divorce it from what is known as astrology, or the science. It was known as a science of astrology, Ilm at-Tanjim at that time. He wanted to divorce astronomy from Ilm at-Tanjim, so he created a new name for this new science that he called Ilm al-Hay'a. And Ilm al-Hay'a is purely mathematical, and so there is no reference to anything that has to do with astrology when it comes to Ilm al-Hay'a. So here is the Tusi couple. What's very important for me that I forgot to mention earlier is in ancient Greek science, it was seen that what was heavenly was perfection. And what was perfection were circular motions, circles, spheres, everything that had to do with spheres and circles depicted perfection. And that only belonged in the heavens. And that down here on Earth, where the world is more corrupt, then we can see linear motion and we can see other types of motion, but never this perfection of circular motion. That only belonged to the heavens. And this is a part of ancient Greek philosophy that actually astronomers preserved all throughout ancient Greek times. And also, I would say that the Muslims continued to extend it, up until when we get to this time period, the 13th century and beyond that. So the Muslims took the work of that was Ptolemy's work. They preserved the ideas of deference and epicycles. So yes, the planets were still glued on the epicycles that rotated, in between the different shells, but they needed to fix that problem that spheres cannot rotate about a point that's off center. So this was the revolutionary idea that Tusi presented, and he said, well, let's fix it by introducing, and he of course presented the mathematical proof for it, because no theorem in math is valid unless you have a proof for it. So he said, we'll take two planar circles. So we're still talking about the epicycle and the deferent. We'll make the epicycle, we'll make the planet attached to the epicycle as Ptolemy suggested before. We will allow the epicycle to rotate in a direction that's opposite of the direction of the deferent circle, where the epicycle, remember, it basically rolls inside the deferent circle. And furthermore, he said, we'll make the epicycle circle rotate twice as fast as the deferent. And what happens is the following. So I'm going to start with the most left square with the diagrams, and I'm going to then move rightward. So if we start with the planet being at this point, then after the red circle rotates half a circle, half a turn, so half a turn, and then the blue circle rotates in the opposite direction, a quarter of a turn, because remember the red circle rotates twice as fast. Then we find that this we'll call it for now planet, would have shifted from this position in the uppermost position further down. So we're talking now linear motion, right? Remember I said that a planet, for example, Venus, there are times when it appears closer to Earth because it's way brighter. It's so bright you think a plane is coming into land. And then there are other times along its cycle where it appears further away. And so now we're talking about using pure circular motion to create linear motion. And so after half a cycle of the red circle and a quarter cycle of the blue, then the planet shifts to this point in the center. And then after another half a cycle of the red circle and a quarter of the blue, then that planet shifts all the way down to the bottom of the circle. And then as that motion continues to happen, then it moves back up towards the center and then back up towards the top. And if you see an animation, the animation here shows you the motion of the epicycle, which is here shown in the blue circle, and the deferent, which is shown in the black circle. The epicycle moves inside the deferent, but twice as fast as the deferent. And as it does so, the planet's motion that is shown here moves back and forth along a straight line. So here is departing from the idea that circular motion only belongs to the heaven, and the corrupt motion, which is linear motion, and it does not fit in the heavens. It really belongs on the planet here, on planet Earth. So anything that's corrupt is part of this planet. Everything that is depicting sheer perfection belongs to the heavens. So here's now producing linear motion out of circular motion. So now mixing the two ideas and no longer separating what the heavens cosmology is from planet Earth. Now, I just want to mention here, and I'll tell you how this fits into the cosmological model that we've mentioned earlier. So this idea using circular motion to produce linear motion, or linear motion to produce circular motion, bears important consequences into our modern era. Because if you think about how an engine works by pistons moving up and down, right? So that's linear motion for the pistons. However, if an engine is sitting inside a vehicle, the vehicle is not moving. What creates the motion of the vehicle is the tires rotating. So we're talking about pistons moving in a linear motion to create a circular motion for the tires, and of course that's through translations from, we have to use gears and etc. And I won't get into those details here, but what I want to point out is the natural philosophy that belonged during the Greek era, where preserving perfection in motion, which is spheres and circular motions to the heavens, and leaving anything else that's corrupt to planet Earth, motion-wise, of course, corrupt is what I mean, now was challenged by a Tusi's couple. So the idea of these circles or these spheres moving about an equant point was divorced permanently, and this is the new way that Al-Tusi introduced his Al-Tusi couple into this model. So the model of the spheres was still preserved, but there was a huge correction in the mathematics that actually allowed a departure from the cosmological ideas that the ancient Greeks produced. So I did this little sketch by hand just to explain to you the difference. And, as a mathematician myself, I really appreciate the accuracy in the mathematics versus, having circles and spheres move about points or rotate about points off center. So if we look at the hashed line, the hashed circle, this was Ptolemy's old crystalline, well, actually not just the crystalline lens for the stars, but also the planets. And here is the equant. So the equant is the point off center where everything had to rotate about it, which was a physical impossibility. But that's the only way he could explain why a planet could be, at point that we call the apogee, which is the furthest away from Earth, or at perigee, where it's the closest away from Earth, and hence give us this distinction in observation when it's very bright or very dim, or bright or dim. When it comes to Venus, it's always bright, but it's brighter and dimmer at different times along its cycle. So what he did, he said, I'm going to introduce the Tusi couple. We call it the Tusi couple. He didn't call it that. So he introduced the Tusi couple that was mounted. So the circle of the Tusi couple was mounted on a new deferent circle. And this new deferent circle is a solid line that's centered on now making the equant a center point. So can circles rotate about a center point? Indeed. Can spheres rotate about a center point? Indeed. So physically, the impossibility of these crystalline spheres to rotate was forever dissolved. And the Tusi couple was mounted on this new deferent circle. And so now you have circles that are rotating about centers. And of course, the Tusi couple allows the planet to come closer, when it's at perigee to Earth, and then allows it to be further away at apogee. And hence, now we have a mathematical theorem that can actually fit observations. Now, this is not the only contribution that happened during Tusi's lifetime and then afterwards. Perhaps the significant contribution that really affected the nature of the astronomical observatory permanently from there on was the introduction of the Maragha Observatory. Now, as I mentioned, the ancient Greeks inherited the Babylonian observations. Yes, al-Battani did his own observations over 41 years, but there was always a need for new observations that spanned the entire period of all of these planets and also the stars. And so there was a need for new observations. And when the Mongols arrived in Persia and they wanted an astrological prediction from At-Tusi, that's why his life was so important to them. He took advantage of their need for new observations and said, well, we actually need to make new observations. And to have new observations, we're going to need to build an observatory. So this was his dream, really, to be able to build an astronomical observatory with larger instrumentations, because up until that time, when we talk about observations, they were maybe observations using smaller instruments. He wanted large, gigantic instruments so that you can have much higher accuracy in the observations. The larger the instrument that's used to observe, the better the accuracy. And so he convinced Hulagu, who was, known as Hulaku in the Arab world, to build the Maragha Observatory. Now, of course, the Mongols were not going to spend their own resources on the observatory, so they actually used waqf money, waqf funds. So these are funds that are usually set aside for building mosques or Islamic schools that would, so it has specific, or they're made to do, they're used for charity purposes. So they're usually funds that are set aside for Islamic purposes. And because the Mongols would not fund the observatory, they actually allocated waqf money or funds to spend on the Maragha Observatory. And that was the first time in history, in Islamic history, that waqf funds are actually spent on something like an observatory, something that is not necessarily specifically directly related to Islamic purposes. So this project was very, very significant. From the get-go, At-Tusi decided to recruit very well-renowned astronomers from all corners of the globe. So we see names like Mu'ayyid al-Ardi, who came from Syria. We say Fao Munji, who came from China. He was recruited by At-Tusi himself. We see Muhyiddin al-Maghribi, who came from Andalusia, or what's known as Islamic Spain, and Qutbuddin al-Shirazi, who was in Persia himself from Shiraz. And so from the very beginning, the Maragha Observatory was an international one in nature because it attracted astronomers from all corners of the globe. The Maragha Observatory introduced some very important scientific research. It actually was a center of scientific research where astronomers from all around the world would actually go to do research there. But not only that, it was a center where students could come to study and would even have scholarships. So the concept of a scholarship to go and study at an institution, goes back to the Islamic era. So under the Maragha Observatory, and of course later on who followed along this school, we have very revolutionary ideas in mathematics. Al-Ardi himself introduced new mathematical ideas that fixed some of Ptolemy's problematic theorems in cosmology, and they were parallel to the ideas that At-Tusi himself presented. And so during this time period, because these mathematical ideas, and because now astronomy emerges as a pure mathematical discipline, George Saliba, who's my mentor and also a renowned world science historian, refers to it as the Maragha Revolution. And all of these main scientists, and I've just mentioned those, the names that are perhaps the most significant in terms of the mathematical theorems they presented, Al-Tusi and Al-Urdi and Al-Shirazi. They created a new tradition in astronomy that other later astronomers followed and became known as the Maragha School. And so this tradition, the Maragha School, extends to later centuries, beyond the 13th century, and we see it as late as the 15th and the 16th century as well. Ibn Ashatir followed along the same ideas that emerged from the Maragha school. He was from Damascus. He was known as the Muwaqqit of the Umayyad Mosque, who would actually know exactly the exact times of prayers, and he would use astronomical observations to do so. And he actually was among those astronomers that invented the idea of what one historian of science, Victor Roberts, referred to as the Copernican model. Even though the Copernican model is, I would say, down to the letter, the same as what Ibn Ashatir introduced and what Copernicus introduced as his new, and it was a hypothesis because Copernicus during that time period wouldn't dare call it anything other than a hypothesis because of the dominance of the Catholic Church at the time over the ideas of science during the Renaissance period. All that Copernicus did was basically reintroduce the ideas that the Maragha school presented in terms of its mathematics that corrected the Ptolemaic model permanently, as I said. And Copernicus then said, well, let's shift the center from Earth to the sun. So, which was really, mathematically speaking, is just introducing a new vector, but it doesn't change the math whatsoever. And that was something known to the Arabs and Muslims at the time, before Copernicus, obviously. But because observations happened from planet Earth, they kept Earth as the center rather than the sun as the center. And I would say center, we know later on it's not at the center when we come to Johannes Kepler. But the Copernican model really just moved the rotation of the planets and the stars rather than around Earth, it was around the sun. So Ibn Shatir followed along the Maragha astronomers. He was in the same school of thought as the Maragha school itself. He was the one who presented an entire body of non-Ptolemaic. So when I say non-Ptolemaic, it's because the idea of spheres rotating about a point that's off center was forever demolished by the new mathematical theorems. And when I say the departure from ancient Greek natural philosophy was because no longer motion that was circular and spherical belonged to the heavens and only that motion, and linear motion was now, part of that with the introduction of the Tusi couple. So the idea of divorcing linear motion from circular and spherical motion in the heavens, but coupling them together using the Tusi couple, that's what really introduced what was a departure from Aristotelian natural philosophy, and also introducing a new non-Ptolemaic model of the heavens. And so, I argue that Copernicus should be considered as someone who continued in the tradition of the Maragha school, because he actually used all the theorems that came out of the Maragha school, one of which, by the way, he was unable to find its mathematical proof, and hence he just presented it without proof, which is, a big no-no for mathematicians. You never present an idea or a theorem without its proof. So one of the things that I wanted to show you that Victor Roberts actually pointed out to us in one of his publications is if we look at the Tusi couple, the way that Tusi himself presented it, so, and then if you look at the same idea presented in Copernicus' work in the 16th century, what I want to point out is not just the resemblance in the, so here's Tusi's couple, right? Here's the circle of the epicycle, and here's the different. But what I want you to notice, especially if you are well versed in the Arabic language, is the lettering. So here is, let's go back to Copernicus' work. Here's the letter G. If we go to El-Tusi's couple that he published, sorry about that, then this is the letter Jim. If we go forward and look at Copernicus's lettering on the epicycle, which is the letter H, and we go back to El-Tusi's couple, we find the letter H as well. So, you know, I talked to my mentor, George Saliba, one time about this, and I said, is it possible that Copernicus had in front of him the translations of these, sorry, not the translations, but the originals of these publications that were written in Arabic, but didn't necessarily have the translations, and someone maybe translated some of it to him. And what he did was he actually copied down to the letter these letters that actually show up in El-Tusi's couple in the original manuscript that showed up then in Copernicus's work. And of course, you know, a lot of historians of science during this Islamic science specifically say that it's very possible that that's what happened, and that's why we see the translations down to the letter that show up again in Copernicus's work. And so we're talking a couple hundred years later, 200-300 years later, we see these ideas show up even with the exact same lettering as they did in the earlier Islamic era. So there were other renowned observatories in the Islamic world. When I mention observatories, there were observatories that lasted maybe a short period of time, 2 or 3 years, etc. And then some that actually lasted longer. The ones that were modeled after the Maragha Observatory are the ones that lasted longer, and the ones that came before were the observatories that were more short-lived, I would say, because they didn't really span the long period of time. And the degree of research and scholarship that happened in those observatories really we didn't really see that level of scholarship and documentation until the modern era. And so if we take a look at this map, you can see where the Maragha Observatory is, which is in northwestern Iran. And what was modeled after Maragha was the Samarqand Observatory, which is in current days Uzbekistan. And then eventually the Istanbul Observatory in current day Turkey. And these three observatories played a really key role, of course the Maragha being the parent one, but they played a really key role in allowing the concept of the observatory as an institution to make its way to Europe and then eventually to the Western world that you know, this presentation is happening in here in the US. And the main and important ideas that emerged out of the Maragha Observatory that allowed the observatory to become an institution were 5 points. So first of all, that you have now a fixed location for an observatory. Before that, observations that took place were over a span of 2 or 3 years, and they were not necessarily at any fixed observatory, but they could happen, you know, observational instruments were small and they can be carried from place to place, and hence observations could be made anywhere. The idea that now we have a permanent location for an observatory allowed for building very large astronomical instruments, and hence allowed for accurate observations. The other very significant, and you know that from our modern era, is without funding, there is no research that can be done, right? And so funding was very important, and Maragha was the very first observatory that actually had funding that allowed it to have observations that spanned longer than 30 years. And I told you the source of that funding at the time, which came from Waqf funds, Islamic Waqf funds, that the Mongols then allocated. Later on, observatories would have maybe a patron who would provide funding, you know, a king or a ruler, etc. The state support today we have in the US federal funding or even private funding, you know, from different donors. But that remains a very key idea for the continuity of the observatory. Without funding, any institution would shut its doors. And Maragha definitely established that as a very important foundation for the observatory. The third point that I want to point out is now that we have a permanent location and now that we have funding, now this observatory allowed for very long-term observations. They were very comprehensive observations. And so that becomes important for the observatory, and current day observatories also require long-term observations because no advancements in astronomy can happen without these long-term observations. And the fourth point is that Maragha Observatory provided an administrative directorship example. So it started with the person of Tusi, Nasir-Din Tusi, and then later on, of course, after he passed away, others then continued in directing the Maragha Observatory, and that model continues to this day. And then lastly, producing astronomical tables that are really comprehensive, and so they can literally document the motions of what we see in the heavens over an entire cycle of these objects that we're observing, rather than do 2-3 years worth of observation as observatories or observations, astronomical observations used to be done before that. Because obviously everyone since ancient times observed the heavens. But to talk about an observatory as an institution, as a model of an institution that was preserved until the modern era, we really go back to the Maragha Observatory. And like I said, the Samarqand and Istanbul ones were modeled after Maragha. And then when we get to the Renaissance era, we see observatories in Europe, such as the Castle Observatory and Tycho Brahe's observatories. These are famous ones. Were all modeled after the Samarkand and Istanbul one. And later observatories, and eventually they influenced, the European ones influenced the American ones. And so, you know, in my master's thesis, when I did my master's in history, my focus was from day one until I graduated was on Islamic astronomy. And my master's thesis was, and I'll show you the front page if you're interested in looking up this particular publication. It's published at the university library where I graduated, University of Missouri, St. Louis. It's titled The History of the Observatory as an Institution, from Maragha to Mount Wilson, which is in California and still is today. And this publication, you know, I was hoping that one day someone would carry the work forward. And one of the things that the University of Missouri St. Louis offers is feedback on when the publications are downloaded and used for research. And so it really pleases my heart to know that almost 600 scholars around the world have been making use of this his thesis to further the work on the history of the astronomical observation as an institution, because it's a very, very significant piece of work that really needs more research done with it, and really needs more ideas and more input from other researchers around the globe, because also of the nature of the observatory as an international institution that remains as such today. And we go back to Maragha for that model itself. So I'm just going to take a few more minutes to share with you a few more slides. This is an example of what is left from the Samarkand Observatory, which is the great arc. The Samarkand Observatory was built later on after Maragha, and it was the grandson of Tamerlane who built it, Ulugh Beg, who was very much a patron of the sciences and loved science. And to this day, this exists in Samarkand, in Uzbekistan. And so they've actually built an entire observatory with its dome, obviously, as a, let's call it a museum, right? So people, when they visit that region, they can actually see what once upon a time this observatory would have looked like. And lastly, I will tell you about astronomical instruments that were used during the Islamic era. When I visited Baghdad in 2002 to visit my late aunt, I remember when I saw this piece of currency, I thought, I know where this is going. That it's going to be in one of my presentations, because of the picture of the astrolabe that shows up on the currency. And that was a very important instrument that was used during the Islamic era, although it was not an Islamic invention. But you know, like I said, the Muslims didn't just take what came before, but they actually improved it, and in some ways even perfected it. Here's another example of the astrolabe, and it comes out of Islamic Spain in the 14th century. And then the spherical astrolabe, that one was, in fact, an Islamic astronomy invention, because the astrolabe that came before that is a planar astrolabe. So it actually is flat, and it's not spherical in its shape. And then quadrants, like the one that we saw in Samarkand. So quadrants in the old days were small, and people can just hold them up by hand. But the one in Samarkand was actually built to, I believe its radius was 25 meters. So that's why a big and permanent observatory would be needed for such an instrument. And then armillaries also were other types of astronomical instruments that were used. And because it was during the Islamic, / Arabic era that these observations were made, then we see names of stars. The catalog of the names of stars has a lot. I would say the constellations were named after the ancient Greeks. The stars were named after the Arabs, because Arabic was the language of science. And so here are just a few examples. In the Taurus constellation, we find the prominent star that is known as Ain, which is the bullseye. In also the Taurus constellation, another star that's also very easily observed is known in English as Aldebaran, but it's Aldebran, which is the follower. In Orion constellation, Betelgeuse, which is perhaps the most referred to star in the Orion constellation, is Beit al-Jawza, the shoulder of Orion. In the Cygnus constellation, Deneb is a star that's named the brightest star, which is Deneb, from Deneb, which is tail in Arabic. In the Auriga constellation, Al-Anz is the name of a star, which is comes from Al-Anz or Ma'iz, is also known. That star name is by the name Ma'iz. And in the Perseus constellation, the star that is also prominent is known as Al-Ghul, which is the demon's eye. And the Draco constellation is Tha'ban. Another one in Orion is Rijal, which comes from the foot, and that's at the foot of Orion, the constellation. And then Fam al-Hut, and then the examples just go on and on. So I'm going to stop sharing at this point, and I'm going to say that in conclusion, what the Maragha School presented to us was a new way of dealing with astronomy as a science. It divorced astronomy from astrology permanently, which is Ilm al-Tanjim, and now we have astronomy as a pure mathematical discipline. And it also, the Maragha Observatory and the school that emerged out of it gave us a model for the observatory that we use until our modern era today. And observatories, even though modern era observatories don't really know that they really go back to their grandparent, which is their great-great-grandparent, the Maragha Observatory. But all aspects of the modern observatory that we would refer to as an institution really emerges from that time period. Thank you. So I'll take any questions that you have. And I don't know if questions are open verbally or if by chat. I'll hand it back to Zaid to do the moderation for questions.
Thank you very, very much, Rihab, for this engaging, mind-opening, and thought-provoking lecture on the great contributions to astronomy made by and in the or during the Arab Muslim civilization eras. I'm particularly fascinated by the accomplishment itself and how it was made at a time when the established knowledge was probably so fossilized, so to speak, that thinking outside the box was difficult. It must have taken a genius to think outside the box. Al-Tusi and his contributions suggest something about the brilliance, really, that must have gone into making this happen. In addition to the benefits that you mentioned, the benefits of seeing the observatory as an institution and not just an instrument or a tool, in addition to these benefits, such as providing funding, providing a location, and so on, providing training for the future scientists and astronomers. This question has been on my mind for a while. I mean, we the moderns like to take pride in what we consider is our contribution to human civilization, as if it is we who have changed everything forever since the start of the Enlightenment in Western Europe and its project, its modernity project. But it seems to me that if it were not for at least in astronomy, we're talking about astronomy, if it were not for those great contributions, those great breakthroughs, if you will, we probably would have stayed where we were 500 to 600 or 700 years ago in the Western world, in terms of dealing with the stars, with the planets. To think that astronomy was closely associated with astrology, I mean, it makes one pity ourselves as if this went on. What should be done? What could be done by scholars who listened to this lecture that you have given and acquired, the knowledge that you are opening this door for us to acquire, what can they do to spread the word in an engaging way? Probably not inside academia, but outside academia. What should one do, especially if the listeners were Arabs or Arab Americans, people like us living in this part of the world, people who have this great heritage, they do not necessarily know about it, or even if they do, they don't know how to go about educating people about it. Is there anything you would recommend here? Is there anything you would say?
So I would say, fortunately, there are more and more publications coming out by historians of science that document, not necessarily I got into a lot of technicalities, obviously, but they document a lot of the contributions of Islamic science to the modern world, really. Because that body of science ushered in the Renaissance. If that didn't happen, a lot of historians of science argue that the Renaissance might have taken way longer to have, or maybe not even at all, to have allowed Europe to come out of the Dark Ages. So to answer your question, I would say, I'm strictly an academic, and that's how I spread the word. But one of my interests is globalizing curricula, and even a subject like astronomy can be, for example, introduced into a class of English, right, as a project where someone would research this topic on Islamic history, and the paper they would present that would actually be on the topic itself, even though they're being graded on their English and their use of English in the course. So globalizing curricula is something that is, I would say, a real necessity. I've been in the forefront of globalizing curricula and helping other faculty across institutions globalize their curricula over 20 plus years. But I would say that would be a way that we can definitely do that academically. In terms of outside of academia, I think social settings like the one, like the Arab American Cultural Center in St. Louis can perhaps do more presentations, and even face-to-face ones in St. Louis throughout the year. It doesn't have to be during Arab culture or Arab American Heritage Month. Book clubs, where I mentioned there are a lot of history of science books now that have emerged, and they're in the dozens, honestly. And I would mention at least my mentor's books, Professor George Saliba, who's now retired from Columbia University, but he's probably the most renowned Islamic science historian in the world. Book clubs would be great. People can gather around to read a book and then discuss it. So these are just some ideas that come to mind.
Thank you. We have a question in the meeting chat box, and I am, of course, inviting everyone here to ask a question or make a comment if they are interested. The question it begins by telling us something about the Arabic letters, that they are uniquely designed to mirror the natural movements and positions of the mouth and throat during speech. And there are examples, of course, such as the letters Ain and Ha and what have you. And then the question is a linguistic question. Are there any other languages in the world with a writing system that visually corresponds to the physical positions of the tongue and throat during pronunciation, as Arabic does? I don't know if this is a question at the heart of your topic, but feel free tell us what you
I would say no, just for the and I'm not a linguist, so I definitely cannot comment on this question from a linguistic perspective. But one of the things that is really striking, and I tell people that in the Arabic language, not just the sounds of the letters, but also the number of words that are produced from those letters, the sheer number of words. There's no other language that comes close to having that number of words out of their letters or alphabet. So Arabic has over 12 million words that are distinct from one another. And when we talk about other languages, we're talking in the hundreds of thousands, not in the millions. And so, yeah, the Arabic language is definitely a very, very rich language. And to even comment on how the pronunciation of the letter and the shape of the letter match visually and also audibly, right? So that's very significant as well. So thank you for that.
speaking of language, I mean, you mentioned the Arab Muslim tradition of translating ancient knowledge from ancient Greece and certainly from other cultures. But you also said that Arabs or Arab Muslim scholars or scholars working at those great Arab Muslim centers did not simply translate, they contributed. Their contributions, and I'm talking here only about the act of translation itself. Do you know of, or are you aware of translations that that went beyond simply translating and presenting the knowledge to people reading in the Arabic language, to opening the door for scientists to use the translated text in ways that the original texts did not allow for, even those who knew the original language. Does that make sense?
Yes. So the example I gave in my presentation is the book of Al-Majasti that became known in its Arabic, but it's really a work of science during ancient Greek era, and it was Ptolemy, Bathlemius, who was the one who basically published his book. But it wasn't published. He didn't publish it as Al-Majasti, but it became known as Al-Majasti. So here is an example to answer your question of that work of astronomy translated into Arabic, but they found it very problematic from a mathematical perspective. And so they went about century after century trying to find a way to fix these mathematical problems, and hence eventually throwing out the Ptolemaic model and creating a non-Ptolemaic model. And we see that across the sciences, all the sciences. We see that in medicine during the Islamic era. Perhaps these two disciplines were the most leading in science during the Islamic era is astronomy and medicine. Although, when we talk about Islamic science, we go to, mathematics is not a science, it's a discipline, but the Muslims definitely made major strides in mathematics during that time period, but also optics and pharmacy, engineering, etc.
Thank you. We have several questions actually coming, and I hope we're not taking a call on you, Professor Sawah. We have a question here that says, how did the Maragha School's mathematical models differ from those of Ptolemy, and in what ways did they challenge Aristotelian cosmology?
So if you remember when I explained the Ptolemaic model, Ptolemy had the spheres, the crystalline spheres that were constructed to explain the motions of the planets and the stars in the heavens. They were mounted, or their motion was about a point that he called the equant, which was an off-center point, which was very, very significant, because that was a problem. And Ptolemy recognized that. How can you have these huge spheres that were rotating, but they're rotating about a point that's off-center? And so in that sense, in fixing that problem is not insignificant. Fixing that problem was a major departure from the Ptolemaic model. So the fact that the astronomers in Maragha, at the Maragha Observatory, were able to produce new models that had circles rotating and spheres rotating about a center point is a very significant departure from the Ptolemaic model. Yes, they kept the deference and the epicycles, but from a mathematical perspective, to change the point about these spheres rotated such that it would make it physically possible. It's a physical possibility for a sphere to rotate about a point off center. It is a physical impossibility for a sphere to rotate about a point off center. So in that sense, they differed from the Ptolemaic model. But then later theorems, and I didn't get into the technicality of the theorems, because what Al-Ardli presented also, Ptolemy's models were all mathematically problematic, and in fact didn't all predict motion of the sun and the moon and all the rest of the 5 planets or 4 planets accurately. And he recognized that, so that's why he left it to future astronomers. But when we talk about what Tusi introduced and what Al-Ardli presented, and I didn't present their theorems because we would get into a lot of technical work that's beyond the scope of this presentation. And what Al-Shirazi did, and then later what Ibn Ash-Shatir presented in terms of his mathematical models, are a complete departure from the theorems and the mathematics presented in Ptolemy's work. And the latest one, which was Ibn Ash-Shatir's work, actually gave us exact predictions of the motions of all of these heavenly objects that Ptolemy couldn't, and explained why their appearance changes, etc. You know, a lot of there is other motion in the heavens we call retrograde motion, where planets like Mercury, like Venus and Mars, they seem to be moving along, you know, moving forward, and then at some point, because of how they rotate around, you know, we know now it's the sun, they appear to be moving backwards and then back forward again, just appearing to move in these retrograde motions. They couldn't be well explained according to the Ptolemaic model to the accuracy that the models presented by the Maragha School did. And then in terms of challenging Aristotelian cosmology weds itself to the heavens are perfect, everything is spherical, circular motion. There is no room in the heavens for the corrupt linear motion that shows up on planet Earth. But Tusi's couple challenged that, because when he introduced his couple and mounted that on the deferent that was now centered on the equant, and the equant was not an off-point center. So now that he introduced the couple and injected it into the model of the heavens of the ancient Greeks, now you have linear motion showing up in the heavens, which did not belong in the heavens. So that was a very important, it opened the door to challenge Aristotelian natural philosophy. So they basically just allowed the door to open ajar, and then eventually, you know, it swung wide open. But someone had to do that, right? Someone had to do the first thing. And so that's what the Maragha School did.
Wonderful, wonderful. Another question from Safwat Walid. He says, has there been any major contributions to modern astronomy done by Arabs or Muslims Or would it be fair to say that the majority of Arab Islamic contribution to astronomy in general was in the time periods you discussed?
So I would say the last contribution that was really significant and ties in with what came before it um, uh, happened in the 16th century. So beyond that, it would be just individual contributions, but not as a school of thought. So, contributions will always happen from people across the globe. But it doesn't mean it falls under the the umbrella of an entire school of thought, which belongs to also a civilization that presented a body of science, an entire body of science during that time period. So, yeah, the 16th century would have been the last one.
Mhm.
And again, they introduced ideas that were still a continuation of the school of thought of the Maragha. They built on the Maragha school to produce new ideas, and they actually the contribution as late as the 16th century allowed for the introduction of the idea of excuse me. I mentioned earlier that I'm overcoming a cold. The introduction of the idea of just pure mathematical constructs, which would be, if I would use modern day language, just like how we have modeling now, mathematical modeling in our modern day, then they also introduce just mathematical constructs to be able to understand the emergence of new ideas in astronomy.
Thank you.
Mhm.
We have a question that probably ties in to what you have just said. Um, what factors led to the decline of the Islamic astronomical tradition, and how might history have unfolded differently if these observatories had continued to evolve?
So that's a very meaty question, very big question. um, and historians differ on what led to the decline of the Islamic astronomical tradition, but I would say not just the Islamic astronomical tradition, but Islamic science in general. Science, and it's perhaps the nature of human beings where everything has a beginning and an end. Nothing has longevity in terms of, the nothing spans the entire length of human civilization. Um, and so, what factors? I'm sure politics played a role. If I use nature as an example, and as I often do, I always like to see examples in nature that allow me to understand some concepts in our everyday life. A fruit, when finally a tree bears fruit, initially it's still in its green form that is still developing and evolving, right? Eventually it becomes ripe to where someone can enjoy its benefits, right? Um, the fruit itself, offers a lot of benefits, and then eventually, if it stays on the tree, it's going to go corrupt and eventually fall to the ground. And so, to me, that's a model of how life happens, and regardless of what the cause is. In that case, it could be excessive sunlight, or maybe you've got the insects that start pitting into or maybe microorganisms in the fruit itself, etc. So I would say just I would use those examples as parallels. What are the microorganisms, and what are the insects, and what are the excessive sunlight, or the birds that eat into the fruit that allow for the decline of its quality, right? And then eventually its demise.
Well, thank you for being as candid as as you have been. I know. I mean, you have been talking and given what the cough that you have probably have taken a toll on you. But can we ask you just one more question? Do you have time for that? Okay. As a physicist and educator, how do you suggest we balance scientific rigor with cultural recognition when discussing historical contributions to science? And probably by extension, or specifically Arab Muslim contributions to science.
So the way that I like to balance those two, the scientific rigor with cultural recognition, is I like to get into the details of the science, because that's important for me to be able to portray an idea. Um, and the cultural recognition is perhaps, to me as a scientist, is secondary to that. Although I would understand from the perspective of the cultures themselves how that becomes important. But, it's important to give credit where credit is due, and whatever and whoever contributes to the advancement of scientific ideas, is, in my view as a scientist, is worthy of shedding light on that, without necessarily overblowing the cultural recognition aspect of it. So, the only reason that we talk about Islamic science in general and call it Islamic and/or Arabic science is because that happened during a time period that is known as the Golden Age of Islam. Just like when we talk about the body of science and philosophy during the Greek era. And so the cultural recognition is important, but to me, it's secondary to the concepts and the ideas that were presented that actually provided a platform for the advancement of uh, human civilization in general.
Thank you very, very much for this wonderful and thought-provoking, really, um, lecture on this important aspect of the contributions that were made by Arabs and under the auspices of the Arab Muslim civilizations and their governing or governments. I appreciate the time you have taken to give us this lecture, and we at the Arab Cultural Center of St. Louis are very happy that we have had you to start this series of lectures celebrating the Arab American Heritage Month. Ladies and gentlemen, we appreciate Professor Rihab Sawah coming to this floor and making this wonderful contribution. She is an Arab American scientist, so she is a contributor following in the steps of the great Arab or Arabic scientists over centuries. Before we wrap up, I would just like to remind our audiences that this series of lectures will continue, and that in 2 weeks, on the 23rd of April, we have another lecture. So please take a look at our announcements regarding these lectures. on Facebook and Instagram. We also would like to let our audiences know that in a few days, on April the 19th, we will have our second annual Arab American Heritage Festival. This will be held at Tower Grove Park, Stone Shelter Pavilion in St. Louis, Missouri. Again, this festival, the second annual Arab American Heritage Festival, will be held at Tower Grove Park, Stone Shelter Pavilion, Saturday, April 19th from 11 a.m. to 7 p.m. This will include art and artwork and music and a book launch exhibit and a painting exhibit, and it's an attempt to showcase something of the rich culture that we have as Arabs living in the United States of America. Thank you, everyone, and thank you, Professor Sawah, and we hope to see you soon. Thank you.
Thank you.